In this section, 5.3, we're going to look at some other problems related to uniform circular motion, that is, in particular, how the centripetal force is balanced by other forces. The first of these problems that we're going to look at has to do with satellites that are in circular orbit. So let's imagine that we have the Earth here. That's the Earth. And out here at some distance, there's a satellite. We want that satellite to stay in orbit. We know that there's a gravitational force if it were just sitting there, and I'm marking now to the center of the Earth. So when I write here radius, I mean the radius from the center of the Earth out to the satellite, because that's where all of the mass of the Earth effectively acts from. And we could have a mass of the Earth, capital M, a mass of the satellite, small m. Your distance r apart, and how are we going to balance that centripetal force? We're going to balance it with the gravitational pull. In fact, if we just sat the satellite there, it would just fall to the Earth. But we're going to move it in an orbit with a tangential velocity, in order to create a centripetal force that will balance it in the other direction. So our gravity, force of gravity, is going to be equal to capital G, small m, large M, over r squared. And then our satellite is going to be moving with some velocity, and so it's going to be small m times v squared, that's the tangential velocity, over the radius r. We can see that we get some nice cancellation here. The small mass doesn't matter. In other words, it doesn't matter what size satellite we have. It does matter what the Earth's mass is, and so forth. Next, this r cancels the r squared here. And now we can compute the velocity, and the velocity is going to be equal to, say, therefore, the velocity is the square root of g times m divided by r. And that's the tangential velocity that a satellite must have in order to stay in a circular orbit. You can say, well, it's kind of hard to know what that is. It's hard to measure that, but it's relatively easy to measure the period. So let's work that problem again. We worked it last time. If you move around in a circle and you're moving with a tangential velocity v tangential, it has a radius r, then we can say the distance around, which is 2 pi r, must equal to the velocity tangential, times the time to go around, and the time to go around is 1 period. So we can convert the tangential velocity into 2 pi r divided by the velocity tangential. Or equivalently, we could put the velocity tangential as equal to 2 pi r over t. We could then take that and plug it in here and compute the period. And if you do that, you'll find a particular period that the satellite has to have if it has a radius r. What would that be? We'd have 2 pi r over t is equal to the square root of g m over r. And if we solve that for t, we would end up with, leave my paper again. We would have, solving for the period, the t would go over here, this would go over here, so we'd have t. The period would be equal to 2 pi r times the square root. I'm going to divide by that, so I flip the square root, times the square root of r over the square root of g times m. Well, that's r to the 3/2 here. So this is 2 pi r to the 3/2 over the square root of g times m. And that would give us the period for the rotation. Also, we can look at artificial gravity, and we've seen that in the movie 2001, where we have a space station, perhaps shaped like a cylinder or as a donut, and has a radius r. And what we want is we want to emulate the gravitational acceleration on this inside surface. So you could walk around, there you go, walk around on this inside surface just as though it's Earth and feel perfectly normal. If you did that, then that acceleration would have to be acceleration due to gravity. Well, how do we get that acceleration due to gravity? It must be v squared over r. Or we can balance it with the forces. We could put an m here and an m here, but they're going to cancel out. So the acceleration due to gravity has to be equal to the centripetal, it's going to be equal to the centripetal acceleration. And again, we can use this to say, at what speed or at what radius do we have to have, or what velocity, in order to get g? And this is the relationship between them. So if you know how large your satellite is in a radius, then that huge tube will have to move around with a tangential velocity given by this equation here. Square root of little g times r. Finally, I want to work another problem that's kind of interesting. As a child, many of you have taken a bucket of water and have tried to impress your friends by taking that bucket of water and rotating it over your head like this without any of the water coming out. Now, as we do that, we could say, okay, as the water goes around the circle, centripetal force up here is going to keep the water from falling on your head. So right up here at the top of the motion, we know that mv squared over r, centripetal force, is going to exactly equal to mg, which is the force due to gravity. So centripetal force upward, gravity downward. If the gravity is greater, the water dumps on your head, and so does the bucket. And you'll notice right here that the mass cancels, and we can compute that v squared. Well, again, it's kind of hard to compute what this v is, the tangential velocity, but we can again go and say, how do we relate that tangential velocity to the period? And the answer is the tangential velocity is equal to 2 pi r divided by the period. So what do we have here? We have to plug this into this, so we would get 4 pi squared r squared over t divided by r is equal to g. Just taken the velocity here and squared it, 4 pi squared r squared over t, over t squared. Almost made that mistake. And I already had an r here in the equation, so there's the r, that is equal to g. The r will cancel with r squared, and I'm interested in computing what t is. So I can bring the t over here and the g underneath, and I will get t is equal to the square root of 4 pi squared r over g, or 2 pi times the square root of r over g. Well, let's roughly see if this makes sense. We can actually test this equation and see if it seems reasonable or not, because you remember what it's like to do this as a child. You can swing that bucket over your head and not have the waterfall. The question is how long should it take for the bucket to go all the way around? That's going to be the period. So that's kind of interesting because you can kind of remember that. Well, let's throw in some rough numbers. Let's assume that r is about equal to 1 meter. Well, that's a little bit long for your arm. We'd say this guy has a long arm. It's 39 inches. Most people, their arm is about, would be something more like a yard. However, we've got the distance of the pail handle out to the water, and so even for people with shorter arms, it's going to be about 1 meter out to the water. So let's assume that r is equal to 1 meter. Our g, as you know, we're approximating it as 10. So what we get is a period in seconds, which is 2 pi square root of 1 over 10. Now, pi is about 3, so twice that's about 6. So very roughly, we have something like about 6 over the square root of 10. Well, 3 times 3 is 9, so we can see that this is a little bit more than 3, but that was a little bit more than 6. So this is going to be very close to 2. I'll let you work out the exact figure. 2 what? 2 seconds. So what I'm claiming is that if you swing this bucket all the way around for a regular adult that has about a 1 yard length between the tip of their fingers and their center of their body, that if you go as fast as 2 seconds for a loop, the water will not spill on you. If you go slower than 2 seconds, a longer period all the way around, it's going to drop on you. Faster is faster than you need to be. So that's about 1, 2, 3, 4, 5, 6, and the water will not spill. So that's kind of an interesting problem, and it gives us an idea of how we resolve forces and compute them with centripetal acceleration.